the flight mechanics subject. And I hope you might have seen the syllabus also, flight mechanics. So the first topic, very first topic is atmospheric properties and standard atmospheric conditions. So without wasting much time, I'm entering into the lecture itself. So the same PPT I have prepared for our session students also. So I have used Professor E.G. Tulapurkara from NPTEL lecture notes. So I hope you might have also seen that NPTEL lecture notes, airplane performance and stability and control. So for GATE exam, I will recommend Professor E.G. Tulapurkara notes itself. Most of the problems and most of the theoretical concept, the questions they have covered from his notes as well as AK Ghosh. Okay, Ghosh from IIT Kanpur. So he is from IIT Madras, and he AK Ghosh lecture notes also there. Airplane performance and stability and control. Okay, so both will be very much good for flight mechanics subject. Okay, so Aishwarya ma'am, shall I start that? Or we have to wait? Okay. Right. So Earth atmosphere. So all the images, all the formulas, all the technical terms I have used from the Tulapurkara notes itself. So this image little bit seems to be like not correct, okay, because the region at this phase is having little bit change, okay. So I will show another image. Okay. Right. So I will explain with the both, but there was some error in this image. So the altitude at this particular point will be little bit constant. Okay, they made in a curvature manner, but it will be a constant. So the temperature is given in the x-axis, and altitude is given in the y-axis, as well as the pressure is given on the other side of the y-axis. Okay, so 0 is here. So positive side and negative. So we have studied this in our schooling itself. What are the layers of Earth atmosphere? So troposphere, stratosphere, mesosphere, ionosphere, or thermosphere we can call that, and exosphere. So 5 layers of Earth atmosphere is there, right? So since this is a basic part, and for flight mechanics as like a introduction for flight mechanics also. So I'm just giving the basic scenario, what is happening in each and every layer of Earth atmosphere. So before entering into that, we should know one thing, that when altitude is measured at different part of world, especially at poles and at equator. So there was little bit change in the troposphere layer. Sorry. So at an altitude of 9 kilometers, if we are at pole, either North Pole or South Pole, if we are measuring the altitude, the tropopause will be at an altitude of 9 kilometers. But when we are in equator, it will be ranging about to 16 kilometers. Okay. So the altitude variation is there. So if you see some graphs, the tropopause will be given with 10 kilometers itself. So here you can see it is above 10 kilometers, right? About 10 kilometers. So there was some contradiction in measuring the altitude and atmospheric conditions. Okay, but always you can fix with a term between 10 to 12 kilometers. That is best for international standard atmosphere condition. Okay. So the first layer, we know that it is troposphere and it is the closest to the Earth's surface and it is characterized by turbulent conditions of air. This and all, everything is very basic and we know that very well, right? So the temperature decreases at this layer, temperature decreases. So if you see here, initially it is in the sea level, it is standard temperature we are having 15 degrees Celsius, right? That is a standard temperature. So the standard pressure is given with 1000 millibar or 1 bar, right? 1000 millibar or 1 bar. So depending upon graphs, it is also changing. Okay. So that is standard sea level parameters. So as altitude increases in the troposphere layer, in the first layer, troposphere layer, the temperature decreases, right? The temperature decreases. What happens to the pressure? Pressure is also decreasing. That we have already experienced. Many of us may have went for hill stations, right? Ride to a hill stations or anywhere like in a particular altitude, right? From the sea level or from the place where we are having. So we may feel that pressure loss and density loss also, right? So if you have went for a trip in nearby hill station, you can easily feel that. So temperature is also decreasing. So how the temperature is decreasing? At what rate the temperature is decreasing? So that is called as lapse rate. At what rate the temperature is decreasing or changing? Not only decreasing, we can say that it is changing. Okay. So that is called as lapse rate. Okay. So at troposphere layer, for 1 kilometer, suppose if I am standing in the sea level and my aircraft is going to fly at 1 kilometer altitude, right? So from the sea level, my temperature will be decreased. So decreased. Okay, so we have to use a sign of minus. So minus sign indicates that decrease in temperature at troposphere. Okay. So minus 6.5 Kelvin per kilometer. Kelvin per kilometer. So that much decrease will happen with 1 kilometer range. Okay. So the highest point of the troposphere is called as tropopause. That we very well know. The highest point of the troposphere layer is tropopause, or we can say the layer which separates troposphere and stratosphere. They will be calling that as tropopause. Okay. So most important thing is this one. This point is very much important, where many countries before finding this 9 kilometer at pole and 16 kilometer at equator, they have taken the readings according to their location. So the countries near to the pole, they have chosen 9 kilometer altitude. The countries with respect to equator, they have chosen around 16 kilometer altitude. So this was regularized by implementing international standard atmosphere. Okay. So previously, the countries, they have chosen their own standards, but when it comes to international standards, so the ICAO, there was an organization called International Civil Aviation Organization is there, ICAO. So they are the one who is authorized to fix international standards. So up to 32 kilometer, the pressure, density, temperature, so those factors are determined by ICAO. Okay, so ICAO is an organization like DGCA. In India, we are having DGCA. In US, we are having FAA, right? So like various country will be having various organizations. So all the organizations will be a member of ICAO. Okay, they will be a member in this organization. Okay. So why this is formed? The main agenda of ICAO is to form the international standards for all the civil aviation. Okay. So how they have determined? Suppose if DGCA is determining one rules and regulations, so it is applicable in Indian boundary only. If DGCA is giving some rules and regulations, it is applicable only in Indian boundary only, right? So like that, Pakistan will have different and Bangladesh will have different. So suppose if an aircraft is taking off from India and if it wants to land in US, some airport, okay. So it has to cross many countries, right? It may cross China, it may cross New Zealand, or it may cross African continent, right? So depending upon the location, right? So the rules and regulations will be varying from one country to another country, depending upon the altitude also, right? So 9-kilometer altitude and 16-kilometer altitude and equator and poles. So in order to avoid this measurement issues, the ICAO has formed the International Standard Atmospheric Conditions, okay, which we are studying right now, and every country is following this International Standard Atmospheric Condition for both aircraft, rotorcrafts, or spacecraft. Okay, but ICAO is having authority to fix with 32-kilometer only, so that is around stratosphere. Okay, so beyond that, every country will be discussing with the space agencies. Okay, so International Space Agency is there, also there. UN is there. So they will be discussing about all those parameters. Okay, so for aircrafts and for our subject, you may know this ICAO is controlling with this International Standard Atmospheric Condition. So the second layer is stratosphere. So it extends up to 50 kilometer. So the stratosphere is also divided into two different categories, like 10 to 30, it will be called as lower stratosphere, where 30 to 50 will be called as upper stratosphere. Upper stratosphere. So what happens to the temperature? So temperature at the lower stratosphere region, it will be nearly constant, but not exactly up to 30 kilometer. It will be around 10 to 20 kilometer. It will be nearly constant. So you can see here, okay, 10 to 20 kilometer will be nearly constant. Okay. So what will be the lapse rate at this particular height? What will be the lapse rate? Since in troposphere we have studied the temperature is decreasing, right? It is decreasing at a rate of minus 6.5 Kelvin per kilometer, right? So at troposphere, at lower stratosphere, that is about 10 kilometer to 20 kilometer, what happens? The temperature is constant. So what will be the lapse rate? The lapse rate will be 0. So lambda indicates lapse rate. Okay, lambda indicates lapse rate. So minus 6.5 Kelvin per kilometer is for troposphere, and this is for stratosphere. So throughout the GATE exam, within this troposphere layer and upper stratosphere layer, your questions will be there mostly. Okay, mostly your questions will be focused with this two particular layer itself. Okay, beyond that they won't ask much about that. If it is a problem, if they are asking a problem on this particular troposphere to solve pressure or temperature or density, so it will be surely less than 30 kilometer altitude. Okay, so we will be also solving today itself, one particular problem. So the next point is what happens to the pressure. So at sea level, the pressure is 1000 millibar. At 10 kilometer altitude or around the tropos pass layer, the pressure is dropped to 100 millibar. So how much it is decreased? In troposphere layer itself, it is decreased by 1/10th of P naught. P naught means sea level density. Okay, P naught means sea level density. So how much it is decreased? 1/10th. 1/10th of P naught. So again in the mid of, that is middle stratosphere region, around 30 kilometer, what happens? Within this 20 kilometer altitude, right, approximately 20 kilometer altitude, again the pressure is dropped by 1/10th of P10 comparing to P10. Okay, P10 means pressure at 10 kilometer altitude. P suffix 10 means pressure at 10 kilometer altitude. The pressure is dropping drastically. Okay, pressure is dropped drastically at the stratosphere region. At the stratosphere region. So this extends from the tropopass to 50 kilometer altitude. So high velocity winds will be encountered, but it is not going to be gusty type. Okay, velocity will be high, but the turbulent effect and that gust effect won't be there. Okay. So temperature remains constant up to 25 kilometer altitude, then it starts to increase. So kindly note it down. So, but in International Standard Atmospheric Graph, they will be given with 20 kilometer altitude, but in book it was written as 25 kilometer. But you can take this itself, 20 kilometer altitude. Okay. So the highest point of the stratosphere is called as stratopass. That we very well know. So the next layer is mesosphere. So in mesosphere, it is extended from the stratopass to 80 kilometer altitude. Okay. So up to 80 kilometer altitude. Here it is little bit 85 around. Okay, 85 kilometer around. Okay, and 60 to 85. Okay, so see that's why I told this book, which was written by Tulapurkara, it was taken with respect to equator because we are located in India. India is located around in the equator region. Okay, so the troposphere will be taken with the highest altitude, so that the mesosphere and all those factors are given with largest value. So if you compare with this graph, it will be showing larger values. Okay. So here you can see that stratopass itself, it is around 49 kilometers. Okay. So another conditions is also there. Geometric height is also there. Okay. So the temperature at the mesosphere decreases to 90 degrees Celsius, minus 90 degrees Celsius. So this is degree, not 0, degree. Okay, minus 90 degrees Celsius in this region. So here you can see stratopass at this particular altitude. It starts to decrease and it reaches up to a value of minus 90 degree Celsius. Minus 90 degree Celsius. So in the mesosphere region, the pressure and density of the air is very low. So you can see the value itself. You can see the value itself. It is around 0.01 millibar. So just if you compare the sea level and the pressure at mesosphere, So you can realize how it is going to have its effect, right? But at this altitude also, we are having little bit molecules. So although the pressure is low, the air is still retain its composition. The molecules will be there, presence will be there, and the air will be still retains. Okay, but it is not going to be good enough for aircrafts. Okay, mass flow rate will be very much less because pressure and density is also very low. So the highest point of mesosphere is called mesomass. Okay, so the layer which separates mesosphere and thermosphere. So the next one is thermosphere or ionosphere. So from the word itself, we can understand that presence of ion will be there, ions and free electrons at this particular altitude will be there. So above 80 kilometer, we are having another one parameter like Kármán line, right? Kármán line. So that will be called as low Earth orbit, LEO, low Earth orbit, 100 kilometer altitude. 100 kilometer altitude. So all those factors like the Burj Khalifa, Mount Everest. Mount Everest is also in troposphere only. So typical airliner. So some passenger aircraft will be flying around the troposphere region itself, right? If it is a Cessna, it will be flying around 5 kilometer maximum altitude will be 5 kilometer, right? So service ceiling, absolute ceiling is also there. So if you see Concorde has flown up to the 20 kilometer altitude, and Blackbird it is reached around 25, and NASA's X-43A that is hypersonic testing vehicle. So that has flown around 35 kilometer. So weather balloons is flown around 40 kilometer, and meteor will be in the mesosphere region. Okay. And you might have seen that aurora, right? So that is also you might have seen already some in social medias, the green lightnings, right? The green lightnings will be there. So that will be in the thermosphere region. So the temperature at this thermosphere, from the term itself, we can understand temperature will be going to be high. Okay, temperature will be going to be high. So from in the mesosphere, the temperature is dropped to the maximum of minus 90 degree Celsius, that is minus 90 degrees Celsius, and then it starts to increase. Okay, so around 150 kilometer, the temperature is reached to 1000 degree Celsius. 1000 degree Celsius. So at 700 kilometer, the temperature is 1780 degrees Celsius. 1780 degrees Celsius. So the temperature is high at this particular altitudes. So when space shuttles are re-entering into Earth atmosphere. Yes.
So I have a small doubt here.
Yes,
So
yes.
it is clearly given that when the altitude is at around 150 kilometers, it's 1000 degrees centigrade. But in the graph, it is well shown that when it is 150 degrees, it is a kilometer, it is only about 40 or 50 degrees centigrade from the graph.
No. Yeah, that's what I told. The graph is having a little bit error in that. Okay, so I will look into that and I will get to that correct graph and I will share you.
Okay, sir.
Okay. But this one, it is now it is followed over. overall with the international standard.
So, but what is the actual temperature, sir? Can you tell it once again?
Sorry?
Actual temperature in thermosphere.
Yeah, that's what the maximum temperature at the thermosphere will be 1780 degrees Celsius.
Okay.
So here also I have made some mistake. So this is degree. So when I use that, I have forgot to mark it as degree. So it was showing us 17,800. Okay. So that is 1780 degrees Celsius at an altitude of 700 kilometers. So some electrical phenomena like aurora borealis will be also occurring in this region. Okay. So actually this is given as 1000 degrees Celsius at 150 kilometer, right?
Yes, sir.
Yes. So that's why they have marked with an arrow. Can you see that?
Yes, sir.
So they have not given with the exact value. They have given with an arrow like it is increasing, which is out of graph. Okay. Which is out of graph. Right? They should have little bit extended that. So for understanding only, they have see here also you can see they have given a marking. Right. Right. So after thermosphere region, we are having exosphere. So this is the outer fringe of air. So in thermosphere region, around 400 kilometers, the International Space Station will be there in thermosphere regions. Okay. So very few molecules are found in this region in exosphere. So gradually we can say that it is for interplanetary space. So after the thermosphere region, that is the thermopass, right? Thermosphere region. So that will be called as exosphere, and it is gradually merges with interplanetary space. So these 5 layers of atmospheric conditions, of course, we are not going to consider mesosphere and thermosphere for aircraft, right? So mostly we will be considering the troposphere and stratosphere. So what is the importance of understanding the international standard atmosphere? So first point is the performance of the airplane is very much dependent on the physical properties of Earth atmosphere. So physical property means temperature, pressure, density. Okay. So depending upon that only, the performance of the airplane can be determined. Okay, it is purely dependent on that. So that's what the first point is. And if we are doing flight testing, so testing of flights, right? Various, suppose if I am integrating a new winglet, for an existing aircraft, so I need to do the flight testing so that I can understand whether the new design will be giving better performance or whether it is safe for all conditions. So that also need to be studied even for a winglet, or if I am changing a new avionic instruments, right? So I need to study about that and I need to do flight testing. So the performance of the same airplane, even for a same airplane, if I am changing any conditions of airplane, right, whether it is a structural or if we are replacing an engine, right, any type of thing we are doing, we need to do the flight testing. So this type of flight testings will be also done by the manufacturer. If, let's say if Boeing or Airbus, if they are manufacturing a new aircraft, they have to do this flight test on different type of days with various atmospheric conditions. I hope you might have seen some flight test videos also. There is a separate job role is also there, flight test engineer. Okay, flight test engineer. It is purely a study with related to airplane performance as well as stability and control. Okay, so flight test engineer role is there. So which represents average conditions prevailing most of the year in Europe and North America. So most of the airplane regulations, suppose if Boeing is developing a new aircraft, they need to get approval from FAA and European European agency ESA. Okay, EASA. So any manufacturer, if they are going for international standard or international customer like connectivity, right, with one airport to another airport, they need to get approval from FAA and EASA. Okay, because these two organizations are playing major role in ICAO. So even DGCA is just following the rules and regulations framed by ESA or FAA. Okay, time to time they will be also changing. Okay, but if there was new laws are implemented, so that will be implemented by FAA and ESA. So it will be followed in ICAO. Then ICAO will suggest for other countries' own civil aviation also. Okay. So simply we can say that we are just copying the rules and regulations from other countries. Okay. But time to time, some rules and regulations will be also framed by Indian government, but it will be applicable only in Indian air boundaries. So as I told, this entire international standard atmospheric condition is given with respect to ICAO, that is prescribed by ICAO. So it is having authority to give the pressure and temperature at mean sea level and variation of temperature up to an altitude of 32 kilometers. Okay. So this is the organization which is regularized the pressure and temperature. So if we are taking off from India and if you are crossing Pakistan and if you are crossing Europe country and if you want to land in US, then by following ICAO regulations, we can easily maintain the same altitude and regulations, pressure difference, right? Pressure and temperature density. So using that only the performance parameters will be measured. Okay, performance parameters will be measured. Okay, that's why the international standard atmospheric condition is very much important. Suppose if you are designing an aircraft for Indian conditions, right? For India's air boundary itself. So then you have to follow Indian atmospheric conditions. So there are some competitions in IIT Bombay also. Right now also they are having a competition in NACDAC. Okay, they called us NACDAC. So for that competition and all, we have to consider with Indian standard atmosphere. Okay, we cannot go with international standard atmosphere. So these things we are very well know that temperature 288.15 Kelvin, 15 degrees Celsius. Pressure is given with respect to 1.01325 into 10 power 5, right? Newton per meter square. And it is given same in the mercury, 760 mm of mercury. Okay. So rate of change of temperature is lapse rate. So at what altitude, how the temperature is varying, either in the troposphere or in the stratosphere. So for our flight mechanics and our gate syllabus, we are only going to cover with to 32 kilometer only, up to 32 kilometer. We are not going to cover beyond that. So the lapse rate at 11 kilometer altitude, it is minus 6.5 Kelvin per kilometer. At 11 to 20 kilometer, the temperature is constant, so it will be 0. Okay, so lambda and lambda at upper stratosphere, that is 20 to 32 kilometer, or middle stratosphere, we can say. This is not upper, this is middle stratosphere. 20 to 32 kilometer, the temperature is rising So it is rising with a lapse rate of 1 Kelvin per kilometer. 1 Kelvin per kilometer. Okay. So this is the important term or important factor you have to remember for your GATE exam. Okay. Suppose if there was a question related to finding pressure or density at particular altitude, so these factors you need to be aware of. Okay, lapse rate.
So in the range of 20 to 32 kilometers, the temperature is rising, right, sir?
Yes.
Okay.
20 to 30 kilometers, they will be rising with a rate of 1 Kelvin per kilometer.
Okay.
So, in order to calculate the pressure and density at various altitude, we will be using the equation of state, basic equation of state, and a hydrostatic equation, right? So that is a very basic equations we will be taking for calculating the pressure and respect to the density, because it is the equation of state itself, it is related with pressure and density and temperature. So dP by dH means change in pressure with respect to change in altitude or change in height. Okay, change in altitude. dP by dH. So from here, if we calculate rho, so rho is given with pressure divided by RT, gaseous constant, right? R. So substitute this in the hydrostatic equation. So the change in pressure divided by pressure at the particular either sea level or particular altitude we can give, and G is gravitational acceleration and dH is altitude and R is gaseous constant and temperature. Okay. So from the basic equation of state and hydrostatic equation, the change in pressure can be calculated. But there was problem with the temperature, right? Because temperature is changing with lapse rate, right? So the lapse rate at troposphere, region, and the temperature can be determined like this. Okay, so what this indicates is T naught is sea level temperature, that is 288.15 Kelvin. Suppose if I want to calculate at 10 kilometer altitude, okay, temperature at 10 kilometer altitude, if I want to calculate, so I have to use T10. So T10 can be calculated with T naught minus lambda H. T naught minus lambda H. So T naught is 288.15 minus lambda is, suppose if you are calculating in troposphere region. So kindly note that down, right? So this condition is given for troposphere, lower stratosphere, middle stratosphere. Okay. So if I am calculating in troposphere region, then I have to use minus 6.5 Kelvin per kilometer. So already in the equation itself, minus is given, right? So you can use the same value, 6.5 into height. That is our 10 kilometer. Okay. So since it is Kelvin per kilometer, so kilometer and kilometer altitude will get cancelled. Okay. So the final value will be our temperature at 10 kilometer altitude. Okay. To calculate temperature at 10 kilometer altitude, we need to use this formula. Not only 10 kilometer altitude, up to 32 kilometer altitude, we can use this formula. Okay. So if I want to calculate up to temperature at 32 kilometers, then I have to use lapse rate with 1 Kelvin, positive 1 Kelvin per kilometer. So if I want to calculate in the lower stratosphere, I have to use 0 Kelvin. So you can multiply with 0 because the temperature is constant. So if you calculate temperature at 11 kilometer or 10 kilometer, that is tropopass. So that will be same up to temperature at 20 kilometer. Okay, if you calculate at temperature 11, that will be same for temperature 20 also in between, because temperature is constant. Okay. So then substituting this equation in the general pressure equation. So from that, we can finally come to a conclusion of calculating pressure and density with this two formulas. Okay. So pressure divided by P naught. P naught is sea level pressure. T naught is temperature at sea level, and all the other factors we are very well know that, right? R is gaseous constant, and G is gravitational acceleration. Lambda, depending upon troposphere region and stratosphere region, we need to calculate. Okay. So here you can see it is given with this was 0.0065 Kelvin per meter. Okay, so you have to be very much careful with the given data, whether the given data is given with altitude is given with kilometer or meter. Okay, so according to that, you have to substitute the values. So if you calculate GR lambda in the troposphere region, so it is given with the value of 5.2558 W. So instead of substituting G lambda R, we can directly substitute this 5.255 W. Okay. So since there was a -1 for density calculation, so we are subtracting that. So this is the final formula if you want to calculate pressure at any altitude, pressure H, density H. Okay. So temperature, the particular altitude. So if H is given, suppose if they have given the aircraft is flying at 12 kilometer altitude, right? So you have to calculate pressure at 12, density at 12. So first you have to calculate temperature, then you can easily calculate the pressure and density. Okay. So we will have a problem right now itself. So with that we can end the session also. Right. So pressure, density, temperature calculations. Okay. So I request all of you to take a paper pen and as well as use your calculator to calculate the values. Right. So I will be giving a problem and I will be asking you to type the answer in the chat. Okay. Okay, before entering into that, we need to see about speed of sound also, right? What happens to the sound, speed of sound at each and every altitude. So the speed of sound at sea level is not going to be same at 10 kilometer altitude also, okay? Because the speed of sound is depending upon the temperature. If sound wants to travel in an surrounding, right? In a surrounding or in an atmospheric conditions. So it is purely depending upon the temperature. Okay. So I hope you may have seen this formula. A is equal to square root of gamma RT. So gamma is 1.4, R is gaseous constant, and temperature. So if I want to calculate speed of sound at 5 kilometer altitude or at 10 kilometer altitude, at any altitude AH, it purely depends upon the temperature at the particular altitude. So if you see at the troposphere region, temperature is decreasing. So what will happen correspondingly? Since speed of sound is directly proportional to temperature, speed of sound will also decrease. Sorry. So when temperature decreases, speed of sound will be also decreasing. Okay. So viscosity. Since we have studied in the troposphere region, temperature decreases, pressure decreases, density decreases, and speed of sound is also decreasing. So the next factor is kinematic viscosity. So I hope you might have heard about Sutherland formula. If you have worked with worked in CFD ANSYS analysis, you might have seen this Sutherland formula. Maybe your professor might have said that use Sutherland formula, right, for calculating the viscosity. So this formula which we have given here, that is to calculate the coefficient of viscosity. This is the formula for Sutherland viscosity formula. The Sutherland formula. So to calculate the coefficient of viscosity at any altitude, okay, mu h, the corresponding temperature need to be determined, and using this formula we can calculate the coefficient of viscosity. So from that the kinematic viscosity can be determined. The kinematic viscosity can be determined. So mu by rho, that we will very well know that kinematic viscosity and coefficient of viscosity, but this formula might be a new for you, right? Sutherland formula. So let's calculate at various altitude, 8 kilometer altitude, this is in troposphere, 16 kilometer altitude, lower stratosphere, 24 kilometer altitude, middle stratosphere. So we will calculate temperature, pressure, density, pressure ratio, density ratio, speed of sound, coefficient of viscosity, kinematic viscosity in international standard atmosphere for 3 different altitudes. Okay. So kindly take a paper pen so we can start solving step by step. Okay. So you have to type the answer in the chat. I will be hiding the answers. So you have to type the answer in the chat box. Okay. So I hope you might have noted down the formulas, right, for pressure and temperature, density. I hope you might have noted down. Let's get into that. So the first step, we are taking 8 kilometer altitude for calculating pressure, density, and all the factors, parameters. Yes?
Sir, can you please show that question slide again?
Yes, yes.
Okay, sir.
Calculate the temperature, pressure, density, pressure ratio, density ratio, speed of sound, coefficient of viscosity, kinematic viscosity at altitudes.
Yes, sir, you can move to the next slide.
Okay. Right. So let's go for the first one, 8 kilometer altitude. So first thing is we need to calculate the temperature. Okay. Whenever we want to solve this type of problems, we need to calculate the temperature at the altitude, because if we calculate the temperature, we can easily calculate the pressure and density and all the remaining factors. Okay. So 8-kilometer altitude lies in the troposphere region. So suppose consider that our aircraft is going to fly at 8-kilometer altitude, and we need to design our aircraft based on the properties, okay, atmospheric properties. So based on that only we can choose our engine. So engine weight, then all the other factors, right? As a designer point of view, if altitude is constrained, so we can say for helicopters, right? It is very much difficult to achieve service ceiling more than 8-kilometer, okay, for helicopters. So if you are have to design a helicopter which can fly about 10-kilometer altitude or about 15-kilometer altitude, right? So then you should know the parameters. Okay, of course, the mass flow rate is not enough for in the stratosphere region, but I'm giving an example. Okay, so if you are going to design an aircraft, so if altitude is a constraint, if there is a constraint between altitude, then you have to know how the parameters, atmospheric parameters are at that particular altitude, and you have to consider some design factors. Okay. So at 8-kilometer altitude, it will be mentioned with T suffix 8, T suffix 8, P suffix 8, rho suffix 8. Okay. So T naught is equal to T minus lambda H. We have seen the formula before. So T is temperature at sea level. T naught is temperature at sea level. T8. Okay, T8. Sorry, here they are both are same only. So they have taken the lambda over there. Both are same only. So T8 is equal to 288.15. That is temperature at sea level. So you can directly use 6.5 Kelvin per kilometer itself. So you can use that. So the final temperature at 8-kilometer altitude is 236.15 Kelvin. 236.15 Kelvin. Okay. So temperature is determined. Since it is troposphere layer, it is now determined. So let's go for calculating the pressure ratio. So the pressure at any altitude, if we are comparing with sea level altitude, the pressure is compared at any altitude at sea level. Okay, ratio between pressure at particular altitude and sea level pressure, then it is called as pressure ratio. Okay, pressure ratio. So it is given with delta suffix 8. Delta suffix 8. Okay, just P8 by P naught. That is pressure ratio at 8-kilometer altitude. So pressure ratio at 8-kilometer altitude is given by temperature at 8-kilometer altitude divided by temperature at sea level. Power 5.25588. Okay. So substitute the value and type the answer in the chat. I request everyone to calculate. Don't just sit idle. So if you are calculating now, it will be very much helpful to remember for your exam. Okay. So calculate now itself. Pressure at 8-kilometer altitude 35 Newton. Okay. Okay. Pressure ratio. Okay. Okay. So same calculate density also. Density at 8-kilometer altitude. Good. So pressure and pressure ratio you have calculated. Good. So pressure ratio is 0.35. Pressure at 8 kilometer altitude is 35,599.5 Newton per meter square. So similarly, calculate the density and density ratio. Density and density ratio. Okay, good. Density ratio is 0.428. Okay, 0.435. Kindly others also try to answer. Okay, so I will show the answer. That is for density ratio. Density ratio is given by sigma. Okay, sigma 8 indicates density ratio. Same like pressure, depending upon the altitude, density ratio is also given. Okay, equal to sigma h. So sigma 8 is equal to rho 8 by rho naught, and it is given with 0.42. So density at that altitude is 0.5256516 meter cube. Okay. So then calculate the speed of sound. Speed of sound at 8 kilometer altitude. Speed of sound. And they calculate the speed of sound value. Okay, 308 meter per second. Good. Okay. So then calculate the viscosity, coefficient of viscosity and kinematic viscosity. Good, Irfan. Calculate the viscosity also. Coefficient of viscosity and kinematic viscosity value. (1.52 into 10 power 5 minus 5). Okay. Okay. So coefficient of viscosity is 1.5268 into 10 power minus 5. So just for kinematic viscosity, mu can be calculated with mu A divided by rho 8. Okay. Mu 8 divided by rho 8. Calculate the kinematic viscosity. (2.9072 into 10 power minus 5 meter square per second). Meter square per second. Okay. Right. So all you need to know is just if you know the temperature at that particular altitude, if you can able to calculate the temperature at that altitude, easily you can derive all the other factors: pressure, density, and pressure ratio, density ratio, and speed of sound. Okay. Easily you can calculate, right? So let's move to the second altitude. So first altitude everyone has done good. So let's move to the next altitude, that is 16 kilometer altitude. So at 16 kilometer altitude, we need to calculate the temperature first, right? At 16 kilometer altitude, we need to calculate the temperature first. So before that, I will just explain one factor about the Mach number. So here they have given, right? So if an aircraft is flying 8 kilometer altitude with a flight speed of 220 meter per second, then the Mach number will be calculated with speed of sound at that particular altitude. Don't calculate Mach number with respect to sea level. Okay. If you know that aircraft is flying at 8 kilometer altitude with a speed of 220 meter per second, you need to calculate the Mach number with respect to the particular height. Don't measure with the sea level altitude. Okay, sea level Mach number. Okay, right? Speed of sound. Speed of sound need to be calculated with particular altitude. Okay. Right. So let's move on to the next altitude, 16 kilometer altitude. That is lower stratosphere region. Lower stratosphere region. So we know one thing, that the temperature at lower stratosphere is constant. We know that it is constant, right? So in order to calculate the constant value at 16 kilometer altitude, if we calculate the temperature at the tropopause altitude of 11 kilometer, tropopause altitude of 11 kilometer, the same is going to be up to 20 kilometer also, right? Because we have studied that temperature is constant from tropopause to 20 kilometer altitude. Okay. So if we calculate the temperature at 11 kilometer altitude, the same is going to be for 12 kilometer, 13 kilometer, or 14 or 16, 18, up to 20, it is same. Okay. So temperature at 11 kilometer altitude will be calculated with temperature at sea level minus lambda. So up to tropopause layer, lambda is varying 0.0065. After this altitude only, it is turning into 0. Okay. So you have to use the lambda up to 11. Up to 11 kilometer altitude, you need to use the lapse rate of troposphere. So that is used as minus 0.065 into 11,000 meter. 11,000 meter. Kilometer it is converted into 11,000 meter. So the temperature at 11 kilometer altitude is 216.65 Kelvin. 216.65 Kelvin. So now if I want to calculate temperature at 16 Kelvin, right? So T naught minus, right? T naught, instead of T naught, I have to use T11. T11 minus 0 into altitude 16. So 0 into any altitude, it will be 0. So temperature at 16 will be equal to temperature at 11. So the same temperature is going to be used for temperature at 16 degree also. So 16 kilometer. 16 kilometer also. Okay. So correspondingly, the pressure 11 kilometer will be calculated. Just we already know the pressure at sea level, right? Pressure at sea level, we already know that. So substitute that value, we can easily calculate the pressure at 11 kilometer and density, corresponding density at 11 kilometer also can be calculated. Okay. Density at 11 kilometer also can be calculated. So what about the pressure ratio and density ratio? Pressure ratio and density ratio. So kindly calculate the pressure ratio and density ratio. So one thing I forgot to inform that the pressure ratio and density ratio, right? So at lower stratosphere region, it will be given with E power, exponential power minus G into H minus 11,000 meter, that is troposphere, divided by RT11. Okay, this is the formula. I forgot to mention that earlier. Okay, that lower stratosphere formula is E power minus G. H is particular altitude 16,000 kilometer, right? 16,000 meter. 16 kilometer, 16,000 meter. Minus 11,000 meter divided by gaseous constant into temperature. Okay. See, we have used previous formula, right?
Excuse me, sir.
Yes, dear.
Sir, can you show that formula once again, sir? I was just
Yeah,
seeing it.
yeah, I will show. So previously we have used the pressure ratio and density ratio with respect to T divided by T naught. So this is troposphere, for troposphere alone. Okay. So this is for stratosphere. Yeah.
Sir, is that P by P11 equal to, is that rho, sir?
This is pressure. This is P naught by P11, rho naught by rho 11. P naught by P11, rho naught by rho 11. This is pressure. This is density.
Okay.
Both are equal. At stratosphere region, inverse of, kindly note that inverse of pressure ratio and density ratio. When I am speaking about density ratio, it has to be rho H by rho naught. Similarly, pressure ratio is pH by P naught. But the formula we are using is P naught by P11, rho naught by rho 11, which means it is inverse of, that is 1 by sigma, 1 by delta. Okay, inverse of density ratio and pressure ratio. Okay, it will be given by exponential power minus. Okay, so substitute that and calculate the values. So you can see the step-by-step procedure, right? So substitute that and type the answer in the chat for pressure ratio and density ratio. 0.4543.
So in the formula, should we maintain it in terms of meters itself, sir, or can we convert it into kilometers? That 11,000
No,
meters.
in the meter itself. Meter itself.
Meter itself. Okay.
Right. Similarly, calculate pressure at 16 degree, 16 kilometer, density at 16 kilometer. Good. Calculate pressure at 16 kilometer, Density at 16 km. Because we have already calculated pressure at 11 km and density at 11 km. Using the previous formula itself, we have calculated pressure at 11 km and density at 11 km. Right? Use that value. Use this value. Use this in this formula. We can calculate pressure at 16 km and density at 16. Pressure 1021.7. Density pressure is 10287 Newton per meter square. Kindly check the density also.
So one small doubt, sir.
Yes, dear.
So like P16 by P11 is equal to T16 by T11, the whole power 5.25588. Can I use that, sir?
For what?
I'm getting
For
confused.
calculating the pressure at 11, right?
Yes, sir. For the pressure at 11.
Pressure at 11, you have to use that because that is the troposphere, right? So at that altitude only the tropopass is ending. So you can use that.
Okay.
Kindly check the density also. Density is correct. Okay. So now calculate the density ratio and pressure ratio. So pressure ratio at 16 means it is given with respect to P16 divided by P0. So this is the correct pressure ratio. So don't get confused between these factors. P16 by P11. This is not pressure ratio. This is just a ratio between 16 and 11 kilometer altitude. Pressure of 16 and 11 kilometer. So when they have given in the question that is pressure ratio, just like that, you have to calculate with respect to sea level condition. Good. Calculate the pressure ratio and density ratios. Zero point 0.167. 0.167 is for density or pressure? Pressure ratio or density ratio? Achha, density you are saying. Okay. Calculate the pressure ratio and density ratio. Pressure is 0.1015. Okay. Good. Density ratio, pressure ratio is done. Okay, density ratio. Okay, dear. Okay, good. So pressure ratio and density ratio is 0.1015, 0.13503. So kindly check that whether the values are correct or not. You are all getting the same value. So if you are done with pressure ratio and density ratio, you can solve for speed of sound at 16 km altitude. Speed of sound at 16 km altitude. Speed of sound 295 meter per second. Okay, 295 meter per second. Yes, 295 meter per second. Good. So similarly, using Sutherland viscosity formula, coefficient of viscosity formula, we can calculate the coefficient of viscosity. So it is around 1.4216 into 10 power minus y. So the kinematic viscosity is value of kinematic viscosity. Eight point five nine, 8.8. Okay, 8.594. 8.594 into 10 power minus 5 meters per second. Okay, right. So now we have calculated for 16 kilometer and 8 kilometer also already done. 16 kilometer we have just now done, right? So the Mach number, if the aircraft is flying at 16 kilometer altitude, then we need to calculate with respect to the 295.07. Okay, Mach number need to be calculated with speed of the aircraft or speed of any object divided by speed of sound at this altitude. Okay, speed of sound at this altitude. Okay, so remember that. Okay, so using the same procedure, we need to calculate for 32 kilometer altitude also. Okay, 32 kilometer also we need to calculate 32 or something like what they are given 24, right?
Yes, sir, 24.
Yeah, 24. So similarly, we have to calculate for 24. But mostly in GATE exam, it is covered with troposphere region. Rarely they have covered with stratosphere. So if you understood this procedure, you can easily able to calculate the pressure, density, and speed of sound and viscosity. Okay. So only one thing I want to say with this comparison. So here you can see the speed of sound is decreasing. Again, it is decreasing. And then at 24 kilometers, it starts to increase. The reason is at this 16 kilometer altitude, temperature is constant. And at this 8 kilometer altitude, temperature is decreasing. But at 24 kilometer altitude, the temperature starts to increase with 1 Kelvin per kilometer. 1 Kelvin per kilometer. So that's why the speed of sound is shown as increased at this particular altitude. Okay. So with this, we will end today's session. Suppose if you are having any queries, we can discuss now. So if you are not having queries, you can leave. If you have any queries, please ask. So I will recommend for flight mechanics, Professor E.G. Tulapurkara's notes, NPTEL lecture only. It is already there in NPTEL. So kindly go and look into that for both airplane performance and stability and control.
Sir, textbook.
Textbook we can prefer J.D. Anderson airplane performance itself.
Okay.